friends, I am Krishna Kanjani from LG Institute of Engineering and Technology. Welcome to the online lecture series on kinematics and theory of machines. In this session, we will learn about belt drives. In previous session, we have derived the equation for length of belt drive, and in this session, we will derive equation for power transmission and belt tension ratio in a flat belt drive. Okay, so let's start with the power transmission equation. So now the amount of power transmitted can be calculated with the can be derived with this basic fundamental that let's consider a driving pulley, that is your pulley number 1 is connected with your pulley number 2, that is your driven pulley. Okay, so now over here we can simply say that while we are transmitting power from one shaft to another shaft, we have to consider the ratio that how much amount of force or how much amount of tension between these belts is making difference. Because let's consider T1 and T2, that is tension in tight side and tension in slack side. If we consider R1 and R2 are the radius of driver and driven, or we can say follower, and let's consider V is the velocity of your belt, that is the final velocity with which your belt is rotating. Okay, so now over here we can say that this belt tension will allow us to transmit power. If we consider that T1 and T2 both are same, if we consider T2 is equal to the same tension that is in T1, so in that case we will not achieve any difference of force over here, and without making any difference of force, how can we calculate the amount of power? Because the basic equation of power can be considered as the change in forces, or we can say the amount of force that is applied on this object with multiplied with the velocity, or we have a simple equation, or we can consider that the unit of power is watt, or we can say it can be written as Newton into meter per second. Okay, so now in that case we can simply say that amount of force into the velocity with which the component is rotating, that will give us the amount of power. Okay, so over here let's consider that the effective change in force, that is difference of force, that is T1 minus T2. Okay, so now the work done per second can be termed as a T1 minus T2 into velocity, or the amount of work which is produced by this belt tension, difference of belt tension is T1 minus T2 into V. Now this is termed as a power transmission if we consider per second. So over here we can simply say that the power transmitted from driving pulley to driven pulley is totally depending upon the belt tensions. Okay, so how much difference of tight side and slack side belt tension we can achieve or we can accommodate in any belt drive will give us the amount of power that we can transmit with the help of that belt drive. Okay, so now similarly with the simple fundamental, we can say that the amount of torque transmitted is nothing but the belt ratio tension into the distance, or we can say force into perpendicular distance will give us the amount of torque. So over here we can say the driving pulley is transmitting torque of T1 minus T2 into R1, and the driven pulley having exerted the torque of T1 minus T2 into radius of that pulley. Okay, now let's derive one most IMP and most important derivation, that is ratio of driving tension in a flat belt drive. Okay, so let's consider a flat belt drive in which your driven pulley or driver pulley is mounted on left side, and your driven pulley is mounted on right side. So over here we have sketched the half section only, that is only if we consider if we draw a sketch of driven pulley. So over here this driven pulley is connected with this belt with two different tensions, that is T1 and T2. Now over here we have to consider this bottom side with T1 tension, that is the tight side, and T2 is known as the slack side. Okay, now we have to calculate the ratio, that how much ratio of T1 and T2, or we can say driving tension tension on tight side to the tension on slack side that we can achieve. Okay, so for that let's consider this diagram in miniature form over here. So So if we draw miniature form of this build, so let's consider a small segment of delta theta over here. So over here, for this delta theta angle, this total angle delta theta, if we sketch this build, then it will make 90-degree angle over here. Okay, so now over here, now for considering this small segment, we can say that for this small segment, the amount of build tension that is on tight side, if we consider as a T, and for slack side, if we consider, for tight side means it have certain amount of extra build tension. So if we consider the T as the initial tension and on both the side, so for tight side we can say T plus delta T is the amount of extra tension, and on slack side it is only T tension. So we can say T plus delta T build tension is acting in perpendicular direction like this, and similarly the small T, only T tension, which is the build tension, acting on the slack side. Okay, so now these two are the build tension terms. Now second one, that is friction. Over here the power transmission is occurring due to the friction between these two components. So over here if we consider the frictional force F is equal to mu into Rn. So over here if we consider the rotation in clockwise direction, so friction force will be in upward direction, because if you consider over here that if you rotating this element in clockwise direction, so your friction will play a role in opposite direction, that is in perpendicular direction to this. So here it will be in a vertical direction, that is frictional force F, and that can be given with the equation mu into Rn. Okay, so here we have understood that T1 and T2 are the tension on tight and slack side, and theta is the angle of contact, that is the whole angle contact theta. Now we have considered a small segment of delta theta angle only, and for that we have assumed T plus delta T tension on tight side, T tension on slack side, and frictional force mu Rn, which is acting in vertical direction. Okay, so now to simplify this arrangement, we can consider that the equilibrium of forces in vertical and horizontal direction. Okay, so if we consider the equilibrium of forces in horizontal direction first. Okay, so for horizontal direction, now we can say that this frictional force is acting mu Rn. So for this mu Rn force, reaction force is perpendicular to this surface, so that is Rn surface. So over here we can say that Rn force, which is acting in horizontal, positive horizontal direction, will produce balance with the help of these two forces, T mu Rn and T plus delta T. Okay, so now here if we take component of this build tension T, then build tension T is making angle delta theta by 2 over here. If you consider the symmetry over here, so over total angle was we have assumed as delta theta, so the half angle is delta theta by 2, and similar angle will produce between these two, that is again delta theta by 2. So over here, so we have to consider the component of this T as T sin theta. Okay, so over here we have to consider, here we have to consider T sin delta theta by 2, that is the horizontal component of this force. Similarly, for the bottom section, we can consider T plus delta T of sin delta theta. Okay, so the second component, that is T plus delta T into sin delta theta by 2. Okay, so in this way we can achieve the horizontal equilibrium equation. Now simplifying this equation, so in this equation if we consider delta theta as a small angle and which is negligible, so we can consider sin delta theta by 2 as only delta theta by 2. Okay, so because for small angle we have basic derivation for that, for a small angle sin theta is equal to c theta, and similarly for cos theta, what we are considering, for small angle of theta we can say cos theta is equal to 1. Okay, remember these two terms because these two terms are required in this derivation. So first, that is sin, for small angle of sin we can consider sin theta is equal to theta, and for cos it is 1. So over here we can replace this sin delta theta by 2 with the simple term delta theta by 2. So by putting this term we can say Rn is equal to T plus delta T of delta theta by 2 plus T of delta theta by 2. So now over here if we simplify this term, then we can say that t into delta theta by 2 into delta t into delta theta by 2. So now here if you consider delta t into delta theta, that is very negligible term. Okay, so if we neglect that term, so now your equation will become t into delta theta by 2 plus t into delta theta by 2. Okay, so by adding these two terms, that is t into delta theta by 2 plus t into delta theta by 2, and neglecting this term, we can say total horizontal equation Rn is equal to t into delta theta. That is your equation number 1, and that is achieved with the help resolving forces in horizontal direction. In similarly, we can resolve these forces in vertical direction also. Okay, so now let's resolve in vertical directions. Okay, so now component for vertical direction, so that is your mu Rn, that is frictional force acting in upward direction. Second, your belt tension component in vertical direction. Now your angle is delta theta by 2 over here, so your side which is adjacent to your angle is termed as a t cos theta. So over here you will get the component in terms of cos. So we can say, resolving these forces in vertical direction, we can say that vertical force mu Rn will be having components t plus delta t cos theta. Now if you consider in upward direction, then it is plus, but if we put this term in opposite direction, then we can consider as a minus of t into cos delta theta by 2. Okay, similarly for lower section, again we can say t plus delta t into cos of your delta theta by 2. So that is your t plus delta t cos delta theta by 2. Okay, so now in this equation we can consider this delta theta as a small angle. So for small angle, we can say consider for cos delta theta by 2 is equal to 1, because as we have learned, for small angle of theta, we can say cos theta is equal to 1. Okay, for small angle of theta, we can simply consider cos theta is equal to 1. So by putting this value in equation, we can say mu into Rn will be equal to t plus delta t, over here replacing with 1, and similarly with 1 over here minus t. So t and minus t. So you have the final equation, that is mu Rn is equal to delta t, or you can say Rn is equal to delta t by 2. That is your equation number 2. Okay, so now we can use this equation number 1 for horizontal and equation number 2 for vertical. Now by equating these two equations, or by putting the value of Rn of this equation in equation number 1, we can say that in equation number 1, that is t delta theta is equal to Rn. So over here we are replacing that t delta theta. Your equation number 1 was t delta theta is equal to Rn. So now over here, if you are replacing this Rn with delta t by 2, so over here your equation will be t delta theta is equal to delta t by mu. So now making arrangement such that t belongs to one side and mu comes with the left hand side. So over here delta t by t is equal to, we can say, mu into delta theta. Okay, so over here we can say that delta t by t is equal to mu into delta theta, and that is the relation of t and theta. Now this equation is useful for this small angle, that is for only delta theta. If you consider the whole arrangement, the total thing, then you have to integrate this equation. Now if you consider the total angle which is in contact with the total angle of your belt which is in contact with the pulley, so for that whole equation you have to take integration on both the sides. Now belt having limitations from T1 to T2 belt tensions, and angle is varies from 0 to theta. So by putting this limit, we can say that integration T1 to T2 delta t by t is equal to mu is considered as a constant term into integration 0 to theta delta theta over here. Okay, so now over here if you integrate this delta t by t in terms of logarithmic term, so it is log of t1 by t2 is equal to mu theta. Okay, so this is the basic equation or the general equation for the ratio of driving tension, or we can say simply, if you put this logarithmic term on opposite side, so over here we can say t1 by t2 is equal to e raised to mu theta. Okay, so this equation is very important and will be useful for any calculations while you are solving the numericals of belt drives. Okay, so in this way we can derive the ratio of driving tensions for flat